We're not going to Mars, at least not anytime soon. That might sound insane given all the hype, the billions invested, and Elon Musk's promises. The dream of Mars is dying slowly, expensively, and in front of our eyes. Mars doesn't want us there. And here is a question. What do you think is the biggest threat to human survival on Mars? Radiation, psychology, or something else entirely? Let us know in the comments. I will pin the most creative answer. Now let's begin. When we talk about sending humans to Mars, we're not discussing a slightly more ambitious moon mission. We're talking about something fundamentally different, a journey that pushes every boundary of human endurance, technological capability, and biological resilience. And here's the unsettling truth. The more we learn about Mars and the journey to get there, the more obstacles we discover. Problems we didn't even know existed 5 years ago are now threatening to derail missions planned for the 2030s. Let me take you back to 1996. Carl Sagan appeared on television, eyes twinkling with that characteristic wonder, talking about Mars with infectious enthusiasm. The plan seemed straightforward then: build a bigger rocket, pack enough supplies, point it at Mars, and off we go. Sure, it would be difficult, but humans had already walked on the moon. How much harder could Mars really be? Well, the answer turns out to be exponentially harder, and not in the ways we initially expected. When engineers first started seriously planning crewed Mars missions in the 1990s and early 2000s, they focused on the obvious challenges. Distance, obviously. Mars is, at its closest approach, around 35 million miles away. That's roughly 150 times farther than the Moon. Duration was another concern. A round trip would take at least 2.5 years, possibly closer to 3 years depending on orbital mechanics and mission architecture. And resources, you'd need to pack everything: food, water, oxygen, fuel for the return journey. But here's where things get interesting. As our technology improved and our instruments became more sophisticated, we started discovering problems layered beneath problems, risks hidden inside other risks. It's like opening a Russian nesting doll, except each doll you open reveals not a smaller doll, but an entirely new category of obstacles you never anticipated. The first major revelation came from radiation studies conducted over the past 15 years. We knew cosmic radiation would be a problem. That was obvious. Space doesn't have Earth's protective magnetic field or thick atmosphere. But the true scope of this challenge only became clear when NASA's Mars Science Laboratory rover, you might know it as Curiosity, carried an instrument called the Radiation Assessment Detector during its journey to Mars in 2011 and 2012. The data that came back shocked researchers. During the transit from Earth to Mars, which lasted approximately 7 months, the Radiation Assessment Detector measured radiation doses that would give astronauts approximately 0.3 millisieverts per day from galactic cosmic rays alone. Now that might not sound like much, but let's put it in perspective. The average person on Earth receives about 3 millisieverts per year from all sources combined: cosmic rays, radon in buildings, medical imaging, everything. An astronaut traveling to Mars would receive that same dose in just 10 days. Over a 2.5-year mission, the minimum time for a round trip plus surface operations, astronauts would accumulate between 600 and 1,000 millisieverts of radiation exposure. Recent studies published in 2025 confirm that this level of exposure increases cancer risk by approximately 1%. But it's not just about cancer risk that emerges decades later. High-energy particles from galactic cosmic rays can penetrate spacecraft hulls and even spacesuits, damaging cells and DNA directly. This can cause acute radiation sickness during the mission itself, cognitive impairment, cardiovascular issues, and even changes at the cellular level that we're only beginning to understand. If you're enjoying this deep dive into space exploration, make sure to give this video a like. Your support genuinely helps us continue creating content that explores the frontiers of human knowledge. Here's where it gets even more counterintuitive, and I want you to appreciate the beautiful paradox of this discovery. Recent research from the European Space Agency and data from the ExoMars Trace Gas Orbiter revealed something absolutely fascinating. The safest time to travel to Mars is actually during solar maximum, when the Sun is most active and volatile. I know what you're thinking. That sounds completely backward, right? When the Sun is throwing solar flares and coronal mass ejections into space like cosmic fireworks, that should be the most dangerous time to travel, shouldn't it? But it turns out the universe has a sense of irony. During solar maximum, the Sun's enhanced activity actually creates a stronger solar wind that sweeps away galactic cosmic radiation coming from beyond our solar system. It's like the Sun generates a protective bubble that partially shields us from the most dangerous radiation. During solar minimum, when the Sun is quiet and calm, that protective effect diminishes, and galactic cosmic rays, which are far more energetic and penetrating than solar radiation, flood through the inner solar system. Scientists have calculated that launching a Mars mission during solar maximum could reduce radiation exposure by approximately half compared to a mission during solar minimum. The challenge: solar cycles last about 11 years, and solar maximum periods are relatively brief and unpredictable in their intensity. This means mission planners have very narrow windows when radiation conditions are somewhat favorable. Miss that window and you're either accepting dramatically increased health risks or postponing your mission for years. And speaking of unpredictability, in February 2026, SpaceX made headlines by postponing its planned uncrewed Mars mission to focus instead on NASA's lunar program. According to reports from the Wall Street Journal, SpaceX informed investors it would delay Mars missions to prioritize developing a lunar lander, targeting an uncrewed moon landing by March 2027. This strategic shift illustrates a fundamental problem facing Mars exploration. The technical challenges keep proving more stubborn than anticipated, forcing companies and agencies to repeatedly push back timelines. One of SpaceX's biggest unresolved challenges is orbital refueling, the ability to transfer cryogenic propellants between spacecraft in orbit. This isn't just a nice-to-have feature, it's absolutely essential for Mars missions. The Starship vehicle that SpaceX is developing for Mars travel is so massive and requires so much propellant that it cannot carry enough fuel to reach Mars and return in a single launch from Earth. Instead, the plan calls for launching the Mars-bound Starship with empty or partially filled tanks, then sending multiple tanker Starships to orbit to refuel it before the journey begins. Sounds straightforward, right? Just space gas stations. But here's the problem: successfully transferring cryogenic propellants, supercold liquids like liquid oxygen and liquid methane, between two spacecraft in the zero-gravity environment of orbit has never been done at the scale required. The fluids behave in bizarre, counterintuitive ways without gravity. They don't pour, they float in unpredictable blobs. They can cause pressure fluctuations that damage tanks. The entire process requires technology that's still in development, and as of May 2026, SpaceX has yet to demonstrate this capability successfully. Blue Origin's lunar lander program faces similar cryogenic fluid management challenges, with their development timeline now running at least 8 months behind schedule, according to a NASA Office of Inspector General report released in March 2026. These aren't simple engineering hiccups. They're fundamental technological barriers that companies are struggling to overcome despite billions of dollars in investment. Now let me take you deeper into another problem that's gotten progressively worse as we've learned more about Mars itself: the Martian environment. From orbit, Mars looks deceptively hospitable. It has polar ice caps, seasons, a 24-hour and 37-minute day that's remarkably similar to Earth's. Early telescope observations in the 1800s led astronomers to speculate about Martian civilizations and canals. Even into the 1960s and 70s, scientists held out hope that Mars might harbor some form of life, perhaps microbial organisms, beneath the surface. But as our robotic explorers have sent back increasingly detailed data over the past 2 decades, a grimmer picture has emerged. Mars isn't just inhospitable, it's actively hostile to human life in ways that make survival there almost absurdly difficult. Let's start with the atmosphere, or rather, the lack of one. Mars's atmosphere is approximately 1% as dense as Earth's. 1%. Imagine standing on the summit of Mount Everest, where the air is so thin that most people require supplemental oxygen. Now imagine air that's 85 times thinner than that. That's Mars. This ultra-thin atmosphere has cascading consequences. First, it provides almost no protection against radiation. Those galactic cosmic rays we discussed. They slam straight into the Martian surface with barely any attenuation. The surface of Mars receives about 24 to 30 microsieverts per hour from galactic cosmic rays during solar minimum conditions. That's roughly 40 times the exposure rate you'd experience on Earth. But wait, it gets worse. Remember when I mentioned we should look at Mars colonization challenges more deeply? If you want to understand just how insurmountable some of these obstacles truly are, I actually created an entire video exploring this topic called Mars Colonization is Impossible. Here is why. I dive into the long-term challenges of establishing a permanent human presence on Mars, the resource limitations, the physiological adaptations required, and the economic realities that make sustaining a Martian colony exponentially more difficult than most people realize. The link is in the description. It really complements what we're discussing here about the journey itself. The thin atmosphere also means temperature regulation becomes a nightmare. Without a thick atmospheric blanket to trap heat, Mars experiences wild temperature swings. At the equator during summer, daytime temperatures might reach a relatively balmy 70 degrees Fahrenheit. Sounds pleasant, right? But that same location will plummet to negative 80 degrees Fahrenheit at night, and in winter or at higher latitudes, temperatures can drop to negative 200 degrees Fahrenheit. These aren't just uncomfortable conditions, they're engineering challenges. Every habitat, every spacesuit, every piece of equipment must withstand temperature variations of 150 degrees or more within a single 24-hour period. Materials expand and contract, seals crack, electronics malfunction, batteries lose efficiency in the cold. Even with the most advanced materials science, designing systems that can reliably operate through these extremes for years without failure is extraordinarily difficult. Then there are the dust storms. Oh, the dust storms. If you've seen the movie The Martian, you might remember the dramatic storm at the beginning that strands Matt Damon's character on Mars. The movie took significant creative license with the intensity of that storm. Martian winds aren't actually strong enough to topple a rocket due to that thin atmosphere, but the dust itself. That's a very real problem, and it's actually worse than the movie portrayed. Martian dust is insidious. It's not like beach sand or household dust. Under microscopes, Martian dust particles appear angular and jagged, almost like tiny shards of glass. These particles are extremely fine, about 1/50th the width of a human hair, and they carry a static electric charge that makes them cling to everything. Spacesuits, solar panels, equipment seals, helmet visors, everything gets coated. During the massive planet-encircling dust storm of 2018, NASA lost contact with the Opportunity rover. The storm blocked so much sunlight that Opportunity's solar panels couldn't generate enough power, and the rover never recovered. That storm lasted for months, covering the entire planet in a haze that turned the Martian sky from its usual butterscotch color to an ominous reddish-brown. For human missions, dust presents multiple critical problems. it degrades solar panel efficiency. Bad news when solar panels are your primary power source. It can contaminate life support systems if it gets tracked into habitats. The static charge and fine particle size mean it infiltrates even well-sealed equipment. And here's something that keeps mission planners awake at night. We don't fully understand what long-term exposure to Martian dust might do to human lungs. Studies of lunar dust brought back by Apollo astronauts showed it was sharply abrasive and potentially toxic. Martian dust may be similarly dangerous, possibly even carcinogenic. Research conducted by NASA's MOXIE experiment, the Mars Oxygen In Situ Resource Utilization Experiment aboard the Perseverance rover, has provided valuable data about producing oxygen from Mars's carbon dioxide-rich atmosphere. MOXIE has successfully produced oxygen 7 times between landing in February 2021 and the end of 2021 and continues to demonstrate this capability. This is genuinely exciting because producing oxygen on Mars is essential for both breathing and rocket propellant. But here's the catch. MOXIE is a small-scale demonstration about the size of a car battery. It produces approximately 6 grams of oxygen per hour. To support a crew of 4 astronauts and produce enough oxygen for a return rocket, you'd need a MOXIE-scaled system about 100 to 200 times larger, running continuously for over a year. That system would need to operate reliably in the dusty, temperature-extreme Martian environment, processing atmospheric carbon dioxide that varies in pressure and composition depending on location and season. Recent modeling studies published in 2023 examined how a full-scale Mars oxygen production system would need to adapt to the changing Martian environment throughout the 14-month operational period required to produce 30 metric tons of liquid oxygen, the amount needed for a return rocket. The challenges are substantial. Atmospheric pressure on Mars varies by up to 25% seasonally as carbon dioxide freezes out at the poles during winter and sublimates back during summer. Dust storm frequency changes with seasons. Temperature fluctuations affect equipment performance. Engineers are essentially trying to design chemical plants that must operate autonomously on another planet in an environment we've only observed from orbit and with a handful of rovers. There's no calling a repair technician when something breaks, and all of this are the radiation, the dust, the temperature extremes, the life support challenges. This is just the environment. We haven't even talked about what the journey itself does to the human body and mind. Let's talk about what happens to you, to your body, your bones, your brain, during the journey to Mars, because this is where the problems cascade into something truly concerning, where the engineering challenges meet human biology in ways that create feedback loops of risk. When astronauts spend time on the International Space Station, they experience microgravity, that weightless environment where everything floats. It looks fun in the videos, doesn't it? Astronauts doing somersaults in mid-air, drinking floating globules of water, sleeping while hovering. But beneath that playful surface, microgravity is waging a silent war on the human body. Your skeleton is constantly remodeling itself. Even right now, as you're listening to this, cells called osteoclasts are breaking down old bone tissue, while other cells called osteoblasts are building new bone. On Earth, gravity provides constant stress on your skeletal system, standing, walking, carrying objects, and this mechanical loading tells your body to keep your bones strong. Remove that gravitational stress, and your body essentially decides it doesn't need all that heavy, metabolically expensive bone tissue anymore. Astronauts on the International Space Station lose approximately 1 to 2% of their bone mass per month in key areas like the hips, spine, and legs. 1 to 2% might not sound dramatic until you realize that's 12 to 24% per year. A Mars mission lasting 2.5 years could result in bone density losses of 30 to 60% in critical skeletal regions. That's approaching the bone density levels seen in severe osteoporosis, a condition where bones become so fragile they can break from minor falls or even forceful sneezes. Now here's the cruel irony that mission planners are grappling with. Astronauts need strong bones for the most dangerous parts of the mission. Landing on Mars involves significant G-forces. Working on the Martian surface, even in Mars's lower gravity, which is 38% of Earth's, requires a skeletal system capable of supporting body weight, plus the mass of a spacesuit, tools, and equipment. And when astronauts finally return to Earth after 2.5 years, they'll experience full Earth gravity again for the first time in years, with a skeletal system that's dramatically weakened. The Soviet cosmonaut Valery Polyakov holds the record for the longest single spaceflight, 437 days aboard the Mir space station from January 1994 to March 1995. When he returned to Earth, despite extensive exercise during the flight, he required weeks of rehabilitation. He could barely walk. His cardiovascular system had adapted to microgravity to such an extent that standing upright on Earth caused severe orthostatic intolerance. His blood pressure would plummet, and he'd nearly faint. And his mission was only 14 months. Mars missions would last roughly twice as long. Current exercise countermeasures aboard the International Space Station include 2 hours of intensive exercise daily using specialized equipment, treadmills with harness systems that simulate body weight, resistance exercise devices, stationary bicycles. This helps, but it doesn't eliminate bone and muscle loss, it merely reduces it. And here's a sobering calculation. For a 3-year Mars mission, astronauts would need to dedicate approximately 2,190 hours, that's 91 full days, just to exercise. That's a significant chunk of crew time that can't be spent on scientific research, equipment maintenance, or mission objectives. But the physical degradation doesn't stop with bones and muscles. Your cardiovascular system remodels in microgravity. Your heart becomes more spherical and loses muscle mass because it doesn't need to work as hard to pump blood without gravity pulling it down toward your feet. Vision problems emerge. Astronauts frequently experience something called spaceflight-associated neuroocular syndrome, where the optic nerve swells and the eyeball becomes slightly flattened due to fluid shifts in the skull. Some astronauts have returned from 6-month missions with permanent vision changes. Your immune system becomes suppressed in space. Studies have shown that viruses that normally remain dormant in your body, like the Epstein-Barr virus or varicella zoster, which causes chickenpox and shingles, can reactivate during spaceflight. Wound healing slows down. The microbial environment changes, with potentially pathogenic bacteria becoming more virulent in the enclosed spacecraft environment, while your body's ability to fight them simultaneously decreases. There's also accumulating evidence of changes at the cellular and molecular level. Telomeres, the protective caps on the ends of your chromosomes, behave strangely in space. NASA's twin study, which compared astronaut Scott Kelly, who spent nearly a year in space, to his identical twin brother Mark, who remained on Earth, found that Scott's telomeres actually lengthened during spaceflight, which was unexpected. But then they rapidly shortened after his return to Earth, potentially ending up shorter than before the mission. We don't fully understand the long-term implications of this, but telomere shortening is associated with cellular aging and increased disease risk. Your circadian rhythms, your internal biological clock, can become severely disrupted. On the International Space Station, which orbits Earth 16 times per day, astronauts experience 16 sunrises and sunsets every 24 hours. On a Mars mission, you'd be traveling through deep space where normal day-night cues disappear entirely. Studies of analog Mars missions here on Earth have documented crew members developing persistent sleep disorders. One crew member, in the 520-day Mars simulation conducted by Russia's Institute for Biomedical Problems, developed chronic insomnia that lasted throughout most of the simulated mission, leading to sleep deprivation, elevated stress hormones, daytime fatigue, and measurable deficits in alertness and reaction time. Sleep might seem like a minor concern compared to radiation and bone loss, but consider this. Sleep deprivation impairs judgment, increases irritability, slows reaction times, and compromises the immune system. An exhausted, irritable crew with impaired decision-making abilities operating complex life support equipment millions of miles from help is a recipe for disaster. This brings us to perhaps the most underestimated challenge of Mars exploration, one that receives far less attention than radiation or bone loss, but might be equally mission-critical: the psychological and behavioral health of the crew. Imagine being sealed inside a spacecraft roughly the size of a small house with 3 to 6 other people, not for a week, not for a month, but for years. You can't go outside, you can't open a window, you can't take a walk in fresh air. Every single moment of every single day, you're breathing recycled air, eating freeze-dried or pre-packaged food, hearing the constant hum of life support machinery, and sharing tight quarters with the same people. Oh, and you're also doing this while traveling through the most hostile environment imaginable, where a single equipment failure could kill everyone aboard within minutes. No pressure. The psychological research on long-duration isolation and confinement paints a concerning picture. A study published in PLOS One examined the 520-day simulated Mars mission I mentioned earlier, the Mars 500 project. 6 healthy males were sealed in a 550 cubic meter chamber. That's about the size of a large house, which might sound spacious until you remember they couldn't leave it for 17 months. The results were illuminating and troubling. The study found substantial individual differences in how crew members responded to the prolonged confinement. One crew member reported symptoms of depression in 93% of mission weeks, with those symptoms reaching mild to moderate clinical levels in more than 10% of mission weeks. Think about that. Clinically significant depression for months on end, with no option to leave, no possibility of early termination, no psychiatric hospitalization available. 2 crew members developed significant sleep-wake timing alterations that began in the first few months and persisted throughout the entire simulation. Their circadian rhythms essentially drifted away from the normal 24-hour cycle. One developed chronic sleep-onset insomnia resulting in persistent partial sleep deprivation. The study also documented conflicts, though interestingly conflicts with mission control, the external support team, were reported 5 times more often than conflicts among crew members themselves. 2 crew members with the highest stress and exhaustion ratings accounted for 85% of all perceived conflicts. This suggests that psychological strain doesn't affect everyone equally, and that a single, stressed, exhausted crew member can create ripple effects throughout the entire team dynamic. Now remember that this simulation took place on Earth. The participants knew intellectually that they could be evacuated in an emergency. They knew that the walls separating them from the outside world were just walls, not the vacuum of space. They knew they weren't being bombarded with cosmic radiation. And still, multiple crew members developed significant psychological and sleep problems. On an actual Mars mission, those safety nets disappear. There is no evacuation option. There is no early termination. If interpersonal conflicts escalate or someone develops a psychiatric emergency, the crew must handle it themselves with only delayed radio communication from Earth for guidance. The communication delay between Earth and Mars is something most people don't fully appreciate until they really think through the implications. Radio signals travel at the speed of light, the fastest anything in the universe can travel. And yet, depending on where Earth and Mars are in their respective orbits, a radio signal takes between 3 and 22 minutes to traverse the distance between the 2 planets. This means a round-trip communication. You send a message, Earth receives it, processes it, and sends back a response takes anywhere from 6 to 44 minutes. Let me put that in perspective. Imagine you're working on critical equipment repair. You're not entirely sure about the next step in the procedure, so you radio mission control for guidance. Now you wait. 6 minutes pass, 10 minutes, 15 minutes. Finally, you receive a response, but by then you've already had to make a decision. Or maybe the situation has changed. Maybe the problem has gotten worse. So you send another message describing the new situation, and you wait again. Every phone call you've ever had, every video chat, every instant message exchange, all of those rely on real-time or near real-time communication. That fundamental aspect of human interaction, that back-and-forth conversational flow, disappears on a Mars mission. Astronauts will essentially be communicating with Earth via very slow email. No spontaneous conversations with loved ones, no real-time technical support, no immediate medical consultation with flight surgeons back home. The psychological impact of this isolation is difficult to overstate. National Geographic reported on the psychological challenges of Mars missions, speaking with researchers including Jane Poynter, who was part of the original Biosphere 2 crew that spent 2 years sealed inside an artificial closed ecosystem environment in Arizona from 1991 to 1993. Poynter emphasized that the communication delay creates a unique form of isolation that has never been experienced by astronauts before. International Space Station crews can have real-time video calls with family. They can watch live sports events. They can participate in real-time interviews. Mars astronauts will have none of that. Dr. Nick Caners, a psychiatry professor emeritus at the University of California, San Francisco, and author of Humans in Space, The Psychological Hurdles, has identified multiple stressors unique to long-duration space missions: confinement, isolation, separation from family and Earth, monotony, and the constant awareness of danger. These stressors interact and compound each other. You're not just isolated, you're isolated while also being confined, separated from loved ones, engaged in repetitive daily tasks, and simultaneously aware that the thin walls of your spacecraft are the only thing between you and certain death. Dr. Suzanne Bell, who leads NASA's Behavioral Health and Performance Laboratory at Johnson Space Center, has stated that for Mars missions, astronauts will need not just technical skills, but also exceptional psychological resilience, conflict resolution abilities, and team cohesion. NASA is using simulated Mars habitats here on Earth, like the SHAPIR program, which stands for Crew Health and Performance Exploration Analog, to study these factors. In these simulations, volunteers live in 3D printed Mars habitat mock-ups for up to a year, following mission timelines and dealing with simulated emergencies, all while researchers monitor their psychological and behavioral responses. But even these sophisticated simulations can't perfectly replicate the psychological reality of being on an actual Mars mission. The volunteers know it's a simulation. They know rescue is available if something goes catastrophically wrong. That knowledge, even if not consciously acknowledged moment to moment, provides a psychological safety net that won't exist on a real Mars journey. NASA's Human Research Program has identified 5 main hazards of human spaceflight: space radiation, isolation and confinement, distance from Earth, altered gravity fields, and hostile or closed environments. Notice that 3 of those 5, isolation and confinement, distance from Earth, and hostile or closed environments, are primarily psychological and behavioral challenges rather than purely physical ones. A 2025 evidence report from NASA's Human Factors and Behavioral Performance Element examined the risk of adverse cognitive or behavioral changes and psychiatric disorders leading to in-mission health and performance problems. The report is sobering. It acknowledges that the prolonged duration of Mars missions, combined with the other stressors, creates an unprecedented psychological risk profile. Previous spaceflight experience, even year-long missions to the International Space Station, may not fully predict how individuals will respond to a 2.5 to 3-year Mars mission. There's also emerging evidence that space radiation itself may affect brain function and mental health. Animal studies have shown that exposure to the types of high-energy particles found in galactic cosmic rays can damage the hippocampus, a brain region critical for memory formation, and may increase anxiety-like behaviors. We don't yet know the full extent of how chronic radiation exposure during a Mars mission might affect cognition, mood, and behavior in humans, but early research suggests it's not benign. Think about the compounding effects here. You have bone loss making you physically weaker. You have radiation exposure potentially affecting your brain function. You have sleep disruption impairing your judgment and emotional regulation. You have isolation and confinement creating chronic stress. You have delayed communication making you feel psychologically separated from Earth. And you have the constant awareness that you're living in a hostile environment where equipment failure means death. Any one of these stresses would be significant. Experiencing all of them simultaneously for years while performing complex technical tasks that require precision and sound judgment, that's the reality of a Mars mission. Now you might be thinking, surely we can engineer our way out of some of these problems, right? Build better radiation shielding, create more comfortable habitats, develop better medical countermeasures? And you'd be right to think that. Scientists and engineers are working on exactly these solutions. But here's where we encounter another layer of problems. The solutions themselves create new challenges. Let's take radiation shielding as an example. The most straightforward way to protect astronauts from cosmic radiation is to put more mass between them and space. More shielding material equals less radiation penetrating to the crew. Simple physics, but here's the problem. Launching mass into space is phenomenally expensive. As of 2026, SpaceX's Starship, which is designed to be the most cost-effective launch system ever built, aims to eventually reduce launch costs to perhaps $1,000 to $2,000 per kilogram to low Earth orbit. That's revolutionary compared to previous systems, but it's still expensive when you're talking about the masses required for effective radiation shielding. Water is actually one of the better radiation shielding materials because hydrogen atoms are effective at absorbing and scattering high-energy particles. To provide meaningful radiation protection for a crew cabin, you'd need water shielding perhaps 20 to 30 centimeters thick, surrounding the living space. For a modest-sized crew cabin, that's tens of metric tons of water that serves primarily as shielding rather than as a consumable resource. Some mission designs propose using the spacecraft's propellant tanks as radiation shielding. Position the tanks between the crew cabin and space so the liquid hydrogen and oxygen propellants provide shielding during the journey. Clever idea, except you're constantly consuming propellant, so the shielding effectiveness decreases over time, and propellant tank placement is constrained by other engineering requirements like center of mass, thermal management, and structural design. Advanced materials like polyethylene or specially designed composite materials offer better shielding per unit mass than aluminum or steel, but they still add significant weight. And here's the catch-22. The heavier your spacecraft, the more propellant you need to accelerate it and decelerate it. More propellant means more mass, which means even more propellant required, which adds more mass. You quickly spiral into diminishing returns where the mission becomes impractically heavy. Some researchers have proposed active shielding systems using magnetic or electric fields to deflect charged particles, essentially creating an artificial magnetosphere around the spacecraft, similar to Earth's natural magnetic field. This sounds like elegant science fiction, and small-scale laboratory experiments have demonstrated the basic principles, but scaling up to provide effective protection for a crewed spacecraft presents enormous engineering challenges. The power requirements are substantial, potentially requiring dedicated nuclear reactors. The magnetic fields strong enough to deflect cosmic rays might also interfere with electronic equipment and navigation systems. And importantly, these active systems don't protect against neutral particles like neutrons produced when cosmic rays interact with spacecraft materials. So we're left with partial solutions. Better shielding helps but doesn't eliminate radiation exposure. Pharmaceutical countermeasures, drugs that might help cells repair radiation damage, are in development but remain unproven for the chronic, low-dose rate exposure scenario of a Mars mission. Improved spacecraft design can create storm shelters, heavily shielded areas where the crew can retreat during solar particle events, but those don't help with the constant background of galactic cosmic rays. The life support challenge presents a similar pattern of problems, creating more problems. Humans are remarkably needy organisms when you think about it. Every single day, each person requires approximately 1 kilogram of food, 2 kilograms of drinking water, and roughly 1 kilogram of oxygen. Those numbers might not sound excessive until you multiply them by crew size and mission duration. For a crew of 4 astronauts on a 30-month Mars mission, that's approximately 3,600 kilograms of food, 7,200 kilograms of water, and 3,600 kilograms of oxygen. That's over 14 metric tons of consumables before you account for any reserves, margins for emergencies, or packaging mass. And remember, this is just to keep people alive. We haven't added spacecraft mass, propellant, scientific equipment, Mars surface equipment, or return vehicle components. The solution, obviously, is to recycle as much as possible. The International Space Station already does this to a remarkable degree. Water from humidity in the air, from astronaut urine, even from their breath and sweat. It's all captured, filtered, purified, and converted back into drinking water. Current systems on the station recover approximately 93 to 94% of water. That remaining 6 to 7% that's lost represents inefficiency in the recovery process and water that remains bound in solid waste. For a Mars mission, you'd need to push recovery rates even higher, ideally approaching 98 to 99%. Those last few percentage points are disproportionately difficult to achieve. Advanced filtration systems, more sophisticated chemical processes, more redundancy to ensure reliability, all of this adds mass, complexity, power requirements, and potential failure points. Oxygen recycling is similarly challenging. The station's oxygen generation system electrolyzes water, splits it into hydrogen and oxygen using electricity. The oxygen is released into the cabin atmosphere, and the hydrogen is vented overboard or, in newer systems, combined with carbon dioxide exhaled by the crew to produce water and methane through a process called the Sabatier reaction. This recovers some of the oxygen that would otherwise be lost, but not all of it. Current systems still require periodic resupply of water to replenish oxygen losses. For Mars missions, engineers are developing closed-loop life support systems that recycle air and water with minimal losses. But closed-loop is somewhat aspirational. Truly perfect recycling with zero losses would violate thermodynamics. Every chemical process, every filter, every pump creates some inefficiency, some loss. The challenge is minimizing those losses while keeping the systems reliable enough to operate for years without resupply. Food presents an even thornier problem. We can't currently recycle food in any practical way. Growing fresh food in space using hydroponic or aeroponic systems is theoretically possible, and experiments on the space station have successfully grown lettuce, radishes, and peppers. But growing enough calories to feed a crew, grains, proteins, fats, not just leafy greens, requires significant space, specialized lighting that consumes substantial electrical power, careful monitoring, and waste management systems to handle plant matter. Some mission architectures propose sending supplies ahead, pre-positioning food, water, equipment, and even return propellant on Mars before the crew launches from Earth. This makes sense from a risk management perspective. If the cargo ship fails to reach Mars or crashes on landing, you cancel or delay the crewed mission. Better to lose cargo than people, but this approach extends mission timelines significantly. Cargo missions would need to launch during one Mars launch window, which occurs approximately every 26 months. Then you'd wait for confirmation that the cargo arrived safely, then launch the crew during the next launch window. That's at least a 26-month delay, possibly longer, between cargo and crew launches. During that waiting period, pre-positioned supplies sit on the Martian surface, exposed to radiation, temperature extremes, and potential dust storm damage. NASA and other space agencies are investigating in situ resource utilization, that elegant acronym ISOU we discussed earlier, to produce consumables on Mars from local resources. The MOXIE experiment on the Perseverance rover has demonstrated that producing oxygen from Mars's carbon dioxide atmosphere is technically feasible. Between February and December of 2021, MOXIE successfully produced oxygen 7 times under varying Martian conditions, different times of day, different seasons, different atmospheric pressures. This is genuinely exciting progress. Producing oxygen on Mars means you don't have to transport all your breathing air and rocket propellant from Earth. For reference, a Mars ascent vehicle, the rocket that would launch astronauts from the Martian surface back to the orbiting spacecraft for the journey home, would require approximately 30 metric tons of liquid oxygen combined with fuel. Bringing 30 tons of liquid oxygen from Earth would require massive cargo spacecraft. Producing it on Mars transforms mission feasibility, but scaling up from MOXIE's demonstration to a production-scale system reveals layers of complexity. A 2023 study published in the journal Space Science and Technology modeled a full-scale Mars ISRU system designed to produce 30 metric tons of liquid oxygen over 14 months. The modeling examined how the system would need to adapt as the Martian environment changes with seasons, dust storms, and daily temperature variations. Mars's atmospheric pressure varies by approximately 25% seasonally. During southern hemisphere winter, carbon dioxide freezes out at the pole, reducing global atmospheric pressure. During summer, that carbon dioxide sublimates back into the atmosphere, increasing pressure. An oxygen production system must handle this variability while maintaining consistent output. Dust storms reduce solar panel efficiency, potentially forcing the system to operate at reduced power. Temperature swings affect equipment performance, particularly pumps, compressors, and cryogenic storage systems. The modeled system would need to operate autonomously or semi-autonomously. Astronauts won't arrive on Mars until after the oxygen is already produced. That's the whole point of pre-positioning. So the ISRU plant must diagnose and potentially fix its own problems for over a year, with only remote monitoring and occasional commanded interventions from Earth, subject to those communication delays we discussed. Reliability becomes paramount. If the oxygen production system fails halfway through its operational period, the entire mission might need to be scrubbed. You can't launch astronauts to Mars without confirmed propellant for their return vehicle. This means building in redundancy, backup pumps, duplicate compressors, multiple filtration systems, which adds mass, complexity, and cost. Water extraction is another ISRU goal. Mars has substantial water ice at the poles and likely buried ice at lower latitudes, but extracting that ice, melting it, purifying it, and producing the quantities needed for both life support and potentially propellant production requires significant infrastructure. You need drilling or excavation equipment, heating systems to melt ice, filtration and purification systems, storage tanks, and again, all of this must operate reliably in the Martian environment. Some proposed mission architectures envision producing methane fuel on Mars in addition to oxygen. Methane and oxygen form an excellent rocket propellant combination. SpaceX's Starship uses methane-oxygen engines specifically because both propellants can theoretically be produced on Mars. The Sabatier process can create methane from carbon dioxide and hydrogen, but you need a source of hydrogen, which likely means electrolysis of water, which means you need substantial quantities of Martian water. Each added capability, oxygen production, water extraction, methane synthesis, multiplies the system complexity and the number of things that can fail. Engineers must balance the mass savings from ISRU against the risks and complexity of the production systems themselves. Now let's add another layer, the Mars landing and ascent challenge. Now, this might sound straightforward. We've landed robots on Mars successfully many times, but landing and launching humans introduces entirely new levels of difficulty. Every successful Mars landing to date has used a combination of heat shields, parachutes, and retropropulsion, rockets firing to slow descent. But the largest object we've successfully landed on Mars is the Perseverance rover, which had a mass of approximately 1 metric ton. A crewed Mars lander would likely have a mass of 20 to 40 metric tons or more, depending on mission design. That's 20 to 40 times heavier. Mars's thin atmosphere is thick enough to cause significant heating during entry, requiring heat shields, but not thick enough for parachutes to provide sufficient braking for heavy payloads. This means any large Mars lander will need powerful retropropulsion systems that fire during the final descent, consuming significant propellant. That propellant mass must be included in the lander mass, which means you need even more propellant to slow the now heavier lander, which makes it heavier still. Another engineering spiral? SpaceX's approach with Starship proposes using the same vehicle for Earth launch, Mars landing, Mars ascent, and Earth return, a fully reusable interplanetary spacecraft. This is ambitious and potentially revolutionary if it works, but it requires that orbital refueling capability we discussed, plus the ability to produce return propellant on Mars through ISRU. Multiple technological capabilities that have never been demonstrated must all work correctly for the mission to succeed. Blue Origin's competing lunar lander program, which could inform future Mars lander designs, is facing development delays related to cryogenic propellant management, demonstrating just how challenging these systems are, even for well-funded, experienced aerospace companies. Landing site selection adds yet another constraint. You want to land somewhere scientifically interesting, preferably with accessible water ice for ISRU. But you also need a landing site that's relatively flat and free of large rocks. You can't risk puncturing a lander leg or tipping the vehicle on rough terrain, and you need low elevation with maximum atmospheric density to help with aerodynamic braking during landing. These requirements often conflict. The most scientifically interesting locations, ancient river deltas, canyon systems, polar regions with exposed ice, are frequently at higher elevations or have rough terrain. Once you've somehow managed to land safely on Mars, and that's a massive somehow given everything we've discussed, you face the challenge of keeping humans alive and productive on the surface. And this is where mission architectures start bumping into some truly intractable problems. Let's talk about spacesuits because they're far more complex than most people realize. The spacesuits used during the Apollo moon landings were engineering marvels for their time, but they were designed for missions lasting a few days with only a handful of moonwalks. Mars missions would require spacesuits capable of much longer operational lifetimes, potentially hundreds of hours of use over 18 months of surface operations. Current spacesuit technology is, frankly, showing its age. The extravehicular mobility units used for spacewalks outside the International Space Station were designed in the 1970s and 80s. They're bulky, difficult to move in, and require significant pre-breathing protocols because they operate at lower pressure than the station's cabin atmosphere. Astronauts must breathe pure oxygen for hours before a spacewalk to prevent decompression sickness, the same bends that scuba divers risk if they ascend too quickly. For Mars, you need suits that are easier to move in, lower torque at the joints for bending and walking. You need suits that can handle the abrasive Martian dust without degradation of seals and bearings. You need suits that can be put on and taken off relatively quickly without lengthy pre-breathing protocols, because conducting frequent geology excursions with hours of preparation before each one would be impractical. And critically, you need suits that are reliable enough to not fail during their operational lifetime, because a spacesuit failure on Mars is immediately life-threatening. NASA's Exploration Extravehicular Mobility Unit, the next-generation spacesuit being developed for Artemis lunar missions and eventually Mars, has been in development for over a decade and has faced repeated delays and budget overruns. A 2023 report from NASA's Office of Inspector General found that the spacesuit program had spent over $1 billion and was still years away from flight-ready hardware. The report noted significant technical challenges including mobility limitations, life support system development, and durability concerns. Axiom Space was awarded a contract in 2022 to develop spacesuits for NASA's Artemis program, with the first units intended for the Artemis 3 lunar landing mission. As of May 2026, that mission has been delayed to no earlier than 2028, in part due to spacesuit development timelines. Think about the implications here. We're planning missions to Mars that might launch in the 2030s or 2040s, yet we're still struggling to develop next-generation spacesuits for lunar missions, and Martian spacesuits will need additional capabilities beyond lunar suits, particularly dust mitigation systems and thermal management for Mars's unique temperature challenges. The dust problem deserves special emphasis because it's been consistently underestimated. During the Apollo 17 mission, astronaut Harrison Schmitt experienced what he called lunar dust hay fever, sneezing, nasal congestion, and irritation after lunar dust was inadvertently brought into the lunar module on spacesuits and equipment. The dust also caused mechanical problems. It abraded suit materials, contaminated seals, and created friction in joints and bearings. Martian dust is potentially worse. It's finer than lunar dust, statically charged, and may contain perchlorates, compounds that are toxic to humans. Studies of Martian soil by the Phoenix lander and Curiosity rover detected perchlorate concentrations of approximately 0.5% by mass. Perchlorates can interfere with thyroid function and, at high exposures, are toxic to the nervous system. A 2022 study published in the journal GeoHealth examined the potential health risks of perchlorate exposure during Mars missions. The researchers modeled various exposure scenarios: inhalation of dust, dermal contact, accidental ingestion, and concluded that perchlorates represent a genuine health concern that will require mitigation strategies. This might include rigorous suit and equipment cleaning protocols before entering habitats, air filtration systems to remove dust particles, and possibly protective measures to limit skin contact with Martian soil. But here's the catch: elaborate cleaning protocols take time and resources. If astronauts spend 30 minutes after each surface excursion carefully cleaning spacesuits and equipment, that's 30 minutes of crew time and overhead for every exploration activity. It also requires water or other cleaning agents, adding to consumable requirements. And despite best efforts, some dust contamination is probably inevitable. The Apollo astronauts discovered that lunar dust got everywhere despite their attempts to contain it. Habitat design must account for this. You need airlocks with excellent sealing, possibly multi-stage airlocks where suits are removed in an outer chamber that can be isolated from the main habitat. You need robust air filtration systems with pre-filters to capture larger particles before they reach finer HEPA filters. You need surfaces that can be easily cleaned and monitoring systems to detect particulate levels in the air. All of this adds mass, complexity, power consumption, and maintenance burden. And remember, habitats must also provide radiation protection, thermal control, life support, power generation, communication systems, medical facilities, exercise equipment, scientific laboratories, food storage, waste management, and living space for crew to maintain psychological health. You're essentially trying to compress a small, self-sufficient town into a few dozen metric tons that can be transported to Mars. Power generation on Mars presents its own challenges. Solar panels work on Mars. We've used them successfully on rovers and landers for decades, but Martian sunlight is only about 43% as intense as sunlight on Earth because Mars orbits farther from the Sun. During dust storms, solar panel output can drop by 75% or more, potentially lasting weeks or months for global storms. Nuclear power systems offer more reliable baseline power, but come with their own complexities. NASA's multi-mission radioisotope. Thermoelectric generators, the nuclear batteries that power rovers like Curiosity and Perseverance, produce only about 110 watts of electrical power from approximately 4.5 kilograms of plutonium-238. A crewed Mars mission would need tens of kilowatts of continuous power, requiring either much larger radioisotope systems or compact fission reactors. NASA's Kilo Power project has been developing small fission reactors in the 1 to 10 kilowatt range specifically for space applications. A successful demonstration test in 2018 showed that the basic technology works, but no space-rated fission reactor has ever flown. Developing flight-qualified systems that are safe to launch, can survive Mars landing, and will operate reliably for years remains an engineering challenge. The combination of solar and nuclear power, solar for baseline needs, with nuclear backup for dust storms or nighttime operations, provides redundancy but requires two complete power systems, doubling mass and complexity in that domain. Let me now shift our perspective and ask a question that doesn't get discussed enough. Why is sending humans to Mars getting worse, specifically now? What's changed in recent years? Part of the answer is that we're learning more. Each robotic mission to Mars returns data that fills in our knowledge gaps, and unfortunately, much of that data reveals new problems rather than confirming optimistic assumptions. Mars is turning out to be more hostile, more variable, and more complex than earlier models predicted. The Curiosity rover's radiation measurements, published in 2013 and refined in subsequent years, gave us our first direct measurements of the radiation environment during a Mars transit and on the Martian surface. Before Curiosity, radiation estimates were based on models and indirect measurements. Curiosity's data showed that those models underestimated certain aspects of the radiation environment. The InSight lander, which operated on Mars from November 2018 until December 2022, detected Mars quakes and gathered data about Mars's internal structure. This was scientifically fascinating, but it also revealed that Mars is seismologically more active than some models predicted. Future Mars habitats will need to withstand not just wind loads and thermal stress, but also potential seismic events. NASA's Mars Reconnaissance Orbiter has observed recurring slope lineae, dark streaks that appear and evolve on Martian slopes during warm seasons. Initially, these were thought to potentially be evidence of flowing liquid water, which was exciting. Subsequent analysis suggested they're probably caused by flowing sand and dust rather than water, which was less exciting scientifically, but also suggested that the Martian surface is more dynamic and potentially unstable in ways that could affect landing site selection and infrastructure placement. We're also discovering that Mars's climate is more variable than anticipated. The 2018 global dust storm that killed the Opportunity rover was not predicted. Dust devils, small whirlwinds that carry dust, are far more common than early observations suggested. The Spirit rover actually benefited from several fortuitous dust devil encounters that cleaned its solar panels, but you can't design a mission based on hoping for favorable dust devils. Beyond the purely technical discoveries, we're also confronting sobering realities about development timelines and costs, and this is where the getting worse aspect becomes particularly acute in the current era. NASA's budget has been essentially flat in inflation-adjusted terms for decades. In 1966, at the peak of the Apollo program, NASA's budget was approximately 4.4% of the total federal budget. Today it's less than half of 1%, roughly 0.4%. In absolute dollars adjusted for inflation, NASA's current budget is substantial, but the agency is trying to simultaneously maintain the International Space Station, develop the Artemis lunar program, continue robotic Mars exploration, support commercial crew and cargo programs, maintain Earth science missions, operate space telescopes, and conduct aeronautics research. Mars missions inevitably get pushed into the future priority category because nearer-term commitments consume available resources. The Artemis program, NASA's initiative to return humans to the Moon, has experienced repeated delays and cost growth. The Space Launch System rocket, which first launched in November 2022 with the uncrewed Artemis 1 mission, had been in development since 2011 and cost over $20 billion through its first launch. The Orion crew capsule has been in development since 2005. Artemis 2, which will send astronauts around the Moon without landing, is currently scheduled for no earlier than April 2027, delayed from an original target of 2024. Artemis 3, the first crewed lunar landing since Apollo, is now targeting 2028 at the earliest. If returning humans to the Moon, which is only 3 days away and which we accomplished over 50 years ago with 1960s technology, is taking this long and encountering these difficulties, what does that tell us about Mars timelines? Some of this relates to genuine technical challenges. We're not simply recreating Apollo, we're building sustainable infrastructure with modern safety standards and reusable systems. But some of it reflects systemic issues in how large aerospace programs are managed, funded, and executed in the 21st century. Cost-plus contracting, where aerospace contractors are reimbursed for their costs plus a profit margin, creates incentives that don't necessarily align with rapid, efficient development. Programs that take longer generate more billable hours and more revenue for contractors. I'm not suggesting malicious intent, but the structural incentives don't reward speed and efficiency the way fixed-price contracts potentially do. SpaceX's approach with Starship represents a different development philosophy: rapid iteration, accepting failures as learning opportunities, privately funded development that doesn't require annual congressional appropriations. The company has conducted multiple Starship test flights, with several ending in dramatic explosions, but each test provided data that informed the next iteration. In June 2024, Starship achieved its first successful controlled re-entry and ocean splashdown during the fourth integrated test flight. The fifth test flight in October 2024 achieved the remarkable feat of catching the Super Heavy booster with the launch tower's mechanical arms, nicknamed chopsticks, demonstrating a key element of the rapid reusability concept. These are genuine accomplishments that have advanced the state of the art. But translating test flights into operational Mars missions requires closing the loop on numerous other technologies: orbital refueling at scale, long-duration life support, reliable ISRU systems, Mars-capable spacesuits, and all the other elements we've discussed. Elon Musk has made characteristically ambitious predictions about Mars timelines, suggesting that uncrewed Starship missions to Mars could occur as early as 2026 and crewed missions potentially in the early 2030s. I want to be clear that I'm not dismissing SpaceX's capabilities. They've accomplished things many experts declared impossible, but I also think we need to be realistic about the difference between achieving orbit and achieving a crewed Mars landing with safe return. A 2025 analysis by Casey Dreyer at the Planetary Society examined Mars mission timelines and concluded that even with aggressive development schedules and adequate funding, the late 2030s or 2040s is more realistic for first crewed Mars landings. This assumes no major technical failures, sustained political and financial support across multiple presidential administrations, and successful development of all necessary technologies. Here's something that doesn't get enough attention. Political sustainability is as crucial as technical feasibility. The Apollo program occurred within a unique political context: Cold War competition with the Soviet Union, a clear deadline set by President Kennedy, and sustained congressional support across both parties. That political environment no longer exists. Modern Mars programs must survive multiple election cycles, changing presidential priorities, and congressional appropriations that can fluctuate year to year. The Constellation program, initiated under President George W. Bush in 2004 to return humans to the Moon by 2020, was cancelled by President Obama in 2010 after spending approximately $9 billion. Elements of Constellation were salvaged and evolved into the current Space Launch System and Orion programs, but years of development time and billions of dollars were disrupted by the policy change. China's space program presents an interesting contrast. The China National Space Administration operates under a different political structure, where long-term programs can be planned and executed across decades without the same electoral cycle disruptions that affect US programs. China successfully landed the Chang'e 4 probe on the far side of the Moon in 2019, the first mission to do so. They returned lunar samples to Earth with Chang'e 5 in 2020 and established the Tiangong space station, which has been continuously occupied since June 2022. China has stated ambitions to land astronauts on the Moon by 2030 and has discussed Mars missions as long-term objectives. A 2023 white paper from the China National Space Administration outlined plans for exploring major scientific questions such as the origin and evolution of the solar system and searching for extraterrestrial life, with emphasis on Mars as a key destination. If China were to announce a specific crewed Mars mission timeline with demonstrated progress toward that goal, it might recreate some of the competitive political dynamics that drove Apollo. But it might also introduce new complexities: international competition rather than cooperation, potential technology export restrictions affecting collaboration, and geopolitical tensions influencing space policy. The International Space Station has been a remarkably successful example of international cooperation in space, with the United States, Russia, Europe, Japan, and Canada working together for over 2 decades despite significant terrestrial political tensions. Whether that model of cooperation can extend to Mars missions, or whether Mars exploration will be characterized more by national competition, remains to be seen. There's also the uncomfortable question of whether human Mars missions are the best use of limited resources for Mars exploration and science. This is somewhat heretical to say in discussions about human spaceflight, but it's worth examining honestly. Robotic missions have been phenomenally successful at exploring Mars. The Perseverance rover is currently collecting samples that a future mission might return to Earth, samples that could potentially contain evidence of ancient Martian life. The Ingenuity helicopter demonstrated powered flight on Mars, opening up new possibilities for aerial exploration. Orbiting spacecraft have mapped the planet in extraordinary detail. All of this has been accomplished at a tiny fraction of what crewed missions would cost. The Perseverance mission, including the rover, the Ingenuity helicopter, launch, operations, and development, cost approximately $2.7 billion. That's a substantial investment, but estimates for crewed Mars missions typically start at $100 billion and go up from there, often well over $200 billion for complete mission architectures with adequate redundancy and safety margins. For the cost of one crewed Mars mission, you could fund dozens of robotic missions, sample return missions, subsurface drilling missions, aerial vehicles, distributed sensor networks, even robotic construction systems that could build infrastructure for eventual human arrival. Dr. Robert Zubrin, president of the Mars Society and one of the most vocal advocates for human Mars exploration, would counter that humans bring capabilities that robots cannot match: adaptability, real-time decision-making, the ability to respond to unexpected discoveries, and fundamentally, the human drive to explore. His book, The Case for Mars, first published in 1996 and updated multiple times since, argues passionately that human Mars exploration is both achievable and essential. Zubrin's Mars Direct architecture proposed a relatively low-cost approach. Send a small crew using efficient mission design, produce return propellant on Mars using ISRU, and accept higher risk levels than NASA traditionally allows. His philosophy is essentially accept that exploration is dangerous, simplify mission design, and just go. There's something appealing about this philosophy, a return to the explorer spirit of earlier eras. But it also runs counter to modern safety culture and risk tolerance. Would the American public accept a Mars mission with, say, a 20% probability of crew loss, a 10% probability? NASA's human spaceflight programs have typically been designed for risk levels well under 1%, though the actual risk, as demonstrated by the Challenger and Columbia disasters, has proven higher than pre-mission estimates suggested. The Space Shuttle program flew 135 missions and suffered two catastrophic failures, Challenger in 1986 and Columbia in 2003, killing 14 astronauts. That's a failure rate of approximately 1.5%, or 1 in 67 missions. If a Mars mission had similar risk levels, would that be acceptable? Mars missions would involve far longer duration, more complex operations, and no possibility of rescue, potentially increasing risk substantially. The ethical dimensions of Mars mission risk deserve more attention than they typically receive. When astronauts board the Space Shuttle or travel to the International Space Station, rescue options exist, at least in theory. The station maintains Soyuz or Crew Dragon spacecraft as lifeboats. Shuttle missions could potentially abort to orbit and wait for rescue, or in some failure scenarios, return to Earth. Mars offers no such options. If something goes catastrophically wrong during the surface mission, a habitat breach, a life support failure, a critical illness or injury, there is no rescue. The crew cannot evacuate to Earth. They cannot wait for a rescue mission because even the fastest possible rescue would take years to organize and execute, involving launch windows, travel time, and all the same challenges we've discussed. A Mars crew that experiences a mission-ending failure will die on Mars, and Earth will learn about it 7 to 22 minutes after it happens, helpless to intervene. This level of risk isn't unprecedented in human exploration. Early Antarctic expeditions knew that once winter set in, they were completely isolated until the following spring. No resupply, no rescue, no communication in many cases. The British Antarctic expedition of 1910 to 1913, led by Robert Falcon Scott, ended with Scott and 4 companions dying on their return from the South Pole, just 11 miles from a supply depot that might have saved them. But modern society has different expectations. We have the technology to communicate instantaneously, to track people in real time, to coordinate rescue efforts globally. The idea of knowingly sending people to a place where we cannot help them if things go wrong challenges contemporary safety culture. Some argue this is precisely why Mars missions are important. They represent a return to genuine exploration where risk is accepted as inherent to the endeavor. Others argue that accepting unnecessary risk when robotic alternatives exist is ethically questionable, particularly when missions are funded by public money and involve national prestige. There's also the question of what happens if, or perhaps when, the first crewed Mars mission encounters a catastrophic failure. The Apollo 1 fire in 1967, which killed astronauts Gus Grissom, Ed White, and Roger Chaffee during a ground test, led to a comprehensive redesign of the Apollo Command Module and a nearly 2-year delay in the program. The Challenger disaster in 1986 grounded the shuttle fleet for 32 months. Columbia's loss in 2003 led to another 2.5-year flight hiatus and ultimately contributed to the decision to retire the shuttle program. A disaster during a Mars mission, particularly if it resulted in a crew dying slowly while Earth watched helplessly, could effectively end human Mars exploration for a generation or more. The political will to continue, the public support to fund subsequent missions, and the willingness of astronauts to accept the risks might all evaporate. This creates a paradox. To make Mars missions acceptably safe, we need extensive redundancy, robust systems, comprehensive testing, and margin for error, all of which add cost, complexity, and timeline. But the longer missions take to develop and the more they cost, the less politically sustainable they become, increasing the likelihood they'll be cancelled before completion. Yet if we cut corners to reduce cost and accelerate timelines, we increase risk to levels that might be politically and ethically unacceptable. Let me address another aspect that's becoming increasingly problematic: planetary protection. This is the discipline of preventing biological contamination between Earth and other worlds, both protecting other planets from Earth organisms and protecting Earth from potential extraterrestrial organisms. For Mars, planetary protection operates under international guidelines established by the Committee on Space Research, COSPAR. These guidelines require that missions to Mars, particularly those investigating potentially habitable regions, must be sterilized to prevent Earth microbes from contaminating Mars and confounding the search for native Martian life. Robotic missions can be extensively sterilized using heat, radiation, and chemical treatments. NASA's Mars 2020 mission underwent rigorous planetary protection protocols. Components were cleaned, sterilized, assembled in clean rooms, and monitored for bioburden, the number of viable organisms present on surfaces. Now consider applying planetary protection requirements to a crewed mission. Humans are walking biomes. Each person carries trillions of microorganisms, bacteria, archaea, fungi, on their skin, in their gut, in their respiratory systems. We shed millions of skin cells daily, each carrying associated microorganisms. We exhale bacteria with every breath. Our waste products are teeming with microbial life. A crewed Mars habitat will be a biologically contaminated environment by definition. Waste management systems will contain Earth organisms. Air filtration systems will capture organic particles. Any breach of the habitat and airlock cycle, a spacesuit that's been outside, creates a potential pathway for organisms to reach the Martian environment. Some argue that Mars's harsh surface conditions, the radiation, the aridity, the temperature extremes, would quickly sterilize any organisms that escaped from habitats. But we've discovered that some Earth organisms are remarkably resilient. Deinococcus radiodurans can survive radiation doses thousands of times higher than would kill humans. Tardigrades can survive vacuum, extreme temperatures, and desiccation. Extremophiles thrive in environments: Antarctic dry valleys, deep-sea hydrothermal vents, acidic hot springs that superficially resemble Martian conditions. A 2023 study published in Frontiers in Microbiology examined the survival of various Earth microorganisms under simulated Martian conditions. The researchers found that while most organisms died quickly, certain species, particularly spore-forming bacteria and some fungi, could survive for extended periods, especially if sheltered from direct UV radiation in cracks, underneath rocks, or in shadowed areas. If Earth organisms established a foothold on Mars, they could potentially spread to subsurface environments where conditions are less harsh, regions with higher humidity, less radiation exposure, and possibly liquid water. This would represent irreversible biological contamination of another planet. It would make detecting native Martian life far more difficult because we'd have to distinguish indigenous organisms from Earth contaminants. And it would violate planetary protection principles that are enshrined in international space law, specifically the Outer Space Treaty of 1967, which requires that space exploration be conducted so as to avoid harmful contamination. Some scientists have proposed that humans should not land on Mars until we've definitively determined whether native Martian life exists. We should conduct extensive robotic exploration, return samples to Earth for analysis, drill into subsurface ice and aquifers, and comprehensively search for biosignatures before we commit the irreversible act of introducing Earth biology to Mars. This is scientifically defensible but creates a temporal paradox for human exploration. The level of exploration needed to definitively answer the life question might take decades, extensive sample return missions, analysis of those samples, follow-up missions to investigate promising locations. By the time we're confident that Mars is either lifeless or that we understand its biosphere well enough to manage contamination risks, the political and financial momentum for human missions might have dissipated. Others argue that we can manage contamination risks through careful protocols, restricting human activities to certain regions, extensively sterilizing equipment that contacts the surface, establishing contamination-free zones around habitats. But enforcement would be challenging. Once humans are on Mars with limited resources and potential emergencies, planetary protection protocols might be subordinated to crew safety and mission success. Let me introduce yet another complication that's emerging from recent research: the psychological effects of the Martian day-night cycle. Mars's day, called a sol, is approximately 24 hours and 39 minutes long. That seems close enough to Earth's 24-hour day that it shouldn't matter much, right? Unfortunately, human circadian rhythms are remarkably sensitive. Research on International Space Station crews and on submarine crews, who also live in environments with artificial lighting and disrupted day-night cycles, shows that even small desynchronization between the internal body clock and the external schedule can cause sleep disruption, fatigue, mood changes, and cognitive impairment. Earth-based studies of people living on Martian time, including NASA mission controllers who sync their schedules to rovers operating on Mars, have documented significant difficulties. A 2014 study published in Sleep Medicine tracked mission personnel during the Mars exploration rover missions, Spirit and Opportunity, and found that despite attempts to synchronize their schedules to the Martian sol, participants experienced chronic sleep deprivation, circadian desynchronization, and increased use of sleep medication. These were people living on Earth with access to natural sunlight during off hours, normal Earth gravity, and the ability to leave their work environment. Mars astronauts would experience the 39-minute drift continuously for 18 months in an artificial environment with no escape and all the other stresses we've discussed. The cumulative effect of living on a 39-minute offset for months could be significant. Some research suggests that chronic circadian disruption increases risks of cardiovascular disease, metabolic syndrome, depression, and impaired immune function. All problems you definitely don't want on a Mars mission where medical resources are limited. Potential solutions include using bright light therapy and melatonin supplementation to help shift circadian rhythms, but these interventions are imperfect. Some mission designs have proposed using rotating crew schedules where different crew members maintain different sleep-wake cycles to ensure continuous operational capability, but this would reduce the time when the full crew is awake and able to work together.